So my name is Ivica Bogosavljević, and this talk is talk about performance price of dynamic memory in C++. The talk is 19 minutes long. During the talk, you can ask questions. In Zoom, there is a question and answer video, so you can ask questions there, and people who want to, the other people can vote that question. So that question which has most votes raises to the top. I see it first. That's one thing, and you can also after the talk, I'm gonna go to the Gather Town. There is a track C room there, and I'm gonna be available there and give answers to any questions that may come up in the follow-up. So let's start. Okay, starting. So about me, my name is Ivica Bogosavljević. I'm an application performance specialist. So application means that I focus on application, not on the systems. So my professional focus is how to make your programs run faster. These include techniques used such as using better algorithms, better exploiting the underlying hardware, better usage of the standard library, how to use your programming language in an efficient manner, and how to configure your operating system. I also write for software performance blog called Johnny Software Lab. There is a link there in the footer. And also I work as a performance consultant. I help developer teams deliver fast software. So let's start. Okay, first thing, a short introduction. When it comes to memory usage in your program, there are basically two kinds of programs. Those programs are nowadays rare. They allocate all the memory in a few large blocks. They typically hold their data in data structures such as array, vectors, or matrices. And for example, many image, audio, and video processing algorithms actually most of the time use this kind of data structures. And we won't talk about these programs today. Today we talk about that more common types of program that allocates many memory chunks during the program's lifetime. If your program has a fast random access data structure, it has a tree or a hash map, it will allocate many small memory chunks, although you might not be aware of that. If you're using C++ vectors to store pointers, so the vectors of pointers, of raw pointers, of unique pointers, of shared pointers in a container, you'll also have many memory allocations, and your program will allocate many memory blocks from the system allocator. Also, if you have classes that have pointers as data members, either raw pointers, unique pointer, shared pointer, you're putting a lot of your program is making a lot of calls to the system allocators. So programs that allocate memory, deallocate memory, or access memory in a random access fashion can suffer from performance degradation. And the focus of today's talk are just exactly these programs. Okay, why is your program that uses dynamic memory slow? So if your program is using, you might ask yourself why. First thing is why, because if your program is allocating and deallocating memory in many small chunks, the performance of the system allocator, the implementation of malloc new and free delete can be a bottleneck. When you profile your program, you will see that your program is spending a lot of time in malloc and free functions. If you access your data structure in a random access fashion, so you have a data structure such as a tree, hash map, allocated objects allocated on heap, the performance of your program can suffer due to data cache misses. Now, if you look at the profiler output, you will see that a certain function is slow, but you won't be able to understand why is this the case? Why is this the case? In that case, if you want to see if your program is suffering due to data cache misses, you need to use specialized profiler tools. On Linux, there is a perfstat or cache grind. I think there are also other tools similar on other operating systems as well. We'll talk about data caches a bit later. Okay, now any questions? If you have any questions, now it's time to ask. You can also ask questions while I'm talking. If not, we move on. Okay, the first part of the talk talks about the performance of memory allocation. So let's talk about that. So a short introduction to the system allocator. So system allocator is an implementation of malloc and free functions that your program uses to get memory from the to get memory and to release to get memory it needs and to release back memory it doesn't need anymore. So please do not confuse system allocators with STL allocators. Internally, how allocators work, so you see this. Internally, they allocate a large block of memory from the operating system, and then they take small chunks from these blocks and then serve it back to your program. Your program uses these smaller chunks to keep its data. So in order for your program to run fast, the allocation algorithm itself also must be very fast. And finding the chunk of available size in memory is not something that can be done really, really quickly. So an example here. So this is one example of how an system allocator might hold its memory, not the only one. So these blocks in green, they are blocks that are used by your program, and the white blocks are free. And there is this linked list which connects all the free blocks. And in worst case scenario, your program it would take some time to find a block, for example, of this size. The system allocator should traverse this list really. It can take some time to traverse this list. So this is sometimes used this kind of allocation scheme, but not always. Okay, moving on. As your program runs, it allocates memory. As time passes, it gets more and more difficult to find the block of appropriate size. What I mean appropriate, not too big, not too small. So as a result, as the time passes, malloc and free or new and delete take more and more time. They take more and more time, and your program is less and less responsive. It's getting slower and slower. So all people who have done development in embedded systems are typically aware of this problem. So here you have a large memory block, and the blocks that are used by your program are in green, and the white blocks are blocks that are available. So if your program wants to find a block which is like 5 or 6 these small blocks, it would have to traverse this list or to have some kind of data structure to allow it to find it fast. So as you can see, the memory fragmentation, the more your program the more your big chunk of memory looks like Swiss cheese, the more it is difficult to find the block of right size. So we talked about memory fragmentation. Now, there are 3 reasons why allocation and deallocation in your programs are slow, and they're represented here in order of importance. If your program is allocating and deallocating a lot of memory, especially small memory chunks. So it doesn't have to do with the allocator itself, it has to do with the way you're using the allocator. If there are memory fragmentation, that's the second reason why your deallocation can be slow. And the third one is if your program is using an inefficient implementation of malloc and free. So your program might be using an inefficient system allocator, and moving to another allocator might help. If you fix any of the above of these reasons, that will make allocation and deallocation in your program faster. If you, for example, if you decrease the number of calls to the allocator, automatically the memory fragmentation will be less pronounced and your program will be more responsive. Okay, questions until now? I don't see any, so moving on. So we talked about 3 principles. Now question is how to apply them in practice. So some programming practices are good for the allocation, for the system allocator, some are bad. So let's talk about those. One of the worst offenders is vector of pointers. So is std vector of raw pointers or std vector of unique pointers, doesn't matter. For each element of an array, there is a call to new or to malloc from the system allocator. So you have one call to new, and when you destroy the data structure, you have one call to delete. Additionally, there is a problem with bad performance due to poor data locality. So neighboring pointers do not necessarily point to neighboring objects in memory, and this can have really, really bad consequences for performance, and we will see that later. How to fix this? There are some alternatives. If the reason why you're using pointers of objects is polymorphism, you can try using separate vector per type. So each type gets its own vector, this decreases tremendously the pressure on the memory allocator, and you have additional benefit that there is a excellent, perfect data locality, and the compiler can do many optimization there because it knows the type at compile time. There is a Boost Poly container is one of the containers that provide you with really efficient and easy to use containers if you need this. Or I wrote also this multi-vector, which is a really simple, small implementation of vector of different types, which use templates instead of runtime polymorphism. So it uses compile time polymorphism instead of runtime polymorphism. The second option is to use the vector of STD variant. This is a good alternative if container needs to be sorted. So the problems with vectors per type is that it doesn't allow you to sort your container as you would like. And STD vector of STD variant allows you that, but it fixes the problem of needing to call the allocator for each element of the vector. And also there is this also really lightweight polymorphic vector that I wrote for this blog post. So you can use it if you need it. The main difference between that one and the STD variant is the STD variant it uses this, let's say, switch statement to figure out the type at compile time, and the polymorphic version uses just the standard virtual function dispatch mechanism. So both of these all approaches that I mentioned here decrease the numbers of calls to malloc tree. Actually, they eliminate them completely, and this also decreases memory fragmentation. So I don't see any questions. I'm moving on. A second solution is to use STL allocator for your data structure. So you have fast access data structures that are based on trees or hash maps, such as STD map, STD list, STD unordered map, allocate a lot of small memory chunks from the system allocator, and this increases memory fragmentation. Alternative is to have a dedicated STL allocator for your data structure. And this has numerous advantages. It uses a bit more memory, but if you have a dedicated STL allocator, then you can make sure that your data structure is allocating memory from a dedicated block. And when the data structure is destroyed, the whole block can be returned back to the operating system. So there is no memory fragmentation if you're using this approach. Additional approach is this STL allocator can be really, really simple. And because it is really simple, it can be really, really fast. So the main reason why you wish to use a custom STL allocator is performance. So no questions, I'm moving on. So here's an example of a custom allocator for an STL container. It's called a zone allocator. So in the constructor, it allocates a large block of memory using mmap. So this works on POSIX compatible systems. And in the structure, returns this huge block of memory using mmap. Now, if you look at the allocate function, it's really, really simple. So we just take the first available chunk of memory from the block. So these are just a few functions. And if you look at the allocate, it's empty. So why it's empty? So we are not in case the data structure is deallocating the chunks, we're not returning them back to the operating system. So because we will return the whole block when the data structure is destroyed and when this zone allocator is also destroyed. This approach is used. For example, I know for sure that the JavaScript engine V8 used in Google, they use this kind of zone allocator. When they create a JavaScript environment, they create a zone allocator, and when they want to destroy, they just destroy all objects at once. That there is no per object destruction. I think that C++. I think that C++17. The C++17 is something called polymorphic memory resources that is really similar to this, and basically this, and I guess in C++17 you should use it. So Jeff asked, presume that the allocator this allocated word. So this zone allocated, this specific implementation doesn't work in a multi-threaded environment, and that's not necessarily a bad thing, because the general purpose system allocator must work in a environment multi-threaded, because it doesn't know how data structure is used. Is it used in one thread, or is it used in several threads? But if you're creating your data structure in one thread and using it in all other threads, then you shouldn't have any problems here, and you get rid of the threading additional burden that's imposed to you by threading. Okay. Moving on. A solution, next solution to memory fragmentation and many calls to malloc and free is not to allocate objects for communication. Well, you often have this pattern. So you have this pattern where there are sender and receiver thread, and they're communicating by sender allocating an object, creating an object, and then sending it to the receiver, and the receiver is deleting the object. Now, most of the allocators don't actually work best when you're allocating an object in one thread and destroying it in another thread. And one of the solution is, and if you have a system that is really busy, so you're producing a lot of objects and sending it to other thread, that can create a lot of calls to the allocator. So one of the solutions is not to release memory back to the allocator, instead of cache it. So there is this class called allocator that can give you a memory chunk, which is uninitialized. And then you call constructor using this syntax. This is C++ syntax. You call constructor on the raw memory chunks. And then when you're done with it, you can call the destructor like this, and then you release memory chunk. And ideally, this allocator class will have an implementation of some kind of pooling mechanism that allows you not to release back chunks to the operating system, but to keep it for some times. This avoids memory fragmentation and makes your program run faster. No questions, moving on. So these are three typical scenarios that often results in using a lot of memories, making a lot of calls to new and free, to malloc and delete, malloc and free, or to new and delete. And what are the and this is I presented ways on how to fix this. Now, there are additional solutions to fight memory fragmentation. One of them is to pre-allocate all the needed memory up front. This is often used in real-time systems, but they don't want to deal with the allocator because they're never sure how much time the allocator actually can take. So they pre-allocate all the memory. If there is a table that can have at most 1,000 entries, they allocate a single table with 1,000 entries. Another way to fight memory fragmentation is to restart the program. And this is also used in the embedded system, and it can be also used in servers. If you have a long-running program that is getting slower and slower, one of the solutions is just to restart it once a day. This works. And you did that back in Windows time. And for example, I know for sure that my television TV box that is used for watching television actually restarts sometime in the morning. And I guess it's the same reason to fix these problems with the memory fragmentation. If your data structure is small most of the time, you can use something called small buffer optimization to avoid small allocation on the heap. The std string does that, and the Boost has a small vector library. If you expect your vector to just hit most of the time to hold up to 4 elements, then you can use this data structure. So how does that work? std string class, until, for example, I think 23 characters, it won't allocate any memory from the heap. When the size of the string is longer than 23, 24 or longer, it will perform the call to new to allocate memory for the string to hold. This is a really nice idea. So if you have this pattern, it works really good. There are some special system allocators that promise low fragmentation. You can try with those. So I mentioned several techniques right now related to decreasing memory fragmentation and decreasing call to new and and delete. Not every technique is presented that I presented is applicable everywhere, so use your good judgment. Questions? I don't see any questions, so moving on. Off-the-shelf allocators. So there is when you compile your program, if you're compiling on Linux, you will get the standard libc system allocators. You will get a standard system allocator, but you can also try a more efficient implementation of system allocators. So no allocators is perfect for all application. You need to test. You need to find the allocator, test it, and verify that it works good with your program. So there are several things to keep in mind if you're trying to replace the standard implementation, libc implementation of malloc and free. First thing is allocation speed. That this is the thing you're most important, you're most interested in when it comes to performance. But there is also memory consumption if the allocator is consuming a lot of memory, because speed and memory consumptions are somewhat related. If you want faster speed, you need to use more memory. Next, memory fragmentation. This is important for long-running applications. So the memory allocator might be great for a short running program, but after several hours, some problems might emerge. And the last thing is data locality. If 2 consecutive calls to malloc return neighboring memory chunks, later when you're traversing the memory chunks, for example, in a vector or linked list, the access speed will be much faster. So if you call malloc 2 times and it returns 2 neighboring memory chunks, that is good for performance. So it's not easy to measure all of these parameters by just measuring runtime, just to let you know. So Alexander Becherikov asked, which STD string implementation are you talking about? So the slide about the STD string. So the STD string in the standard library, I think it's the part of the libstd C++ and also libc++, that implementation uses small string, small buffer optimization or small string optimizations. So you can Google it and see. So it's nothing new and nothing fancy. Okay. Moving on. So off-the-shelf allocator. As I already said, standard C library will provide the implementation of malloc and free. New and delete in C++ use malloc and free from the standard system C library, and these are most commonly available on Linux. There are other allocators on Linux that you can install from repositories. One is by Google called tcmalloc, one is by Facebook, gemalloc, one is by Microsoft, memalloc. There is a Horde allocator, ptmalloc, dlmalloc. So you see every big vendor has its own allocator, and I think the reasons is they have their own reasons why is that. Each allocator makes certain trade-offs for speed and memory consumption. There is no good nor bad. You need to try to measure speed, measure memory consumption, and measure it in the long-running environment and see which one suits you best. So I did some experiments with the allocator. Earlier, I used to present this in the terminal, but I think it's better just present it as a slide. Allocators come as libraries, and you can either link your program against those libraries or replace them in runtime. So you don't have to recompile your program, you can replace it on runtime. This is on Linux only. So on Linux, there is this LD preload environment variable to override default allocator, and use it like this. Use LD preload, and then you specify location for the library. In this case, it's libtcmalloc, and then you call your program regular with all the arguments. So we tested a few allocators for performance, and here are the results. So first thing important to note is what we tested. We tested Kaldi speech recognition software. So it's open source, you can download it, and it puts a large pressure on the system allocator. 7.7% of the time is spent in malloc and 1.5 is spent in free. So this is a single-threaded program, and it uses linked list to store data. Now, linked list puts a large pressure on the memory allocator. So what are the right times? The built-in takes 27 milliseconds, tcmalloc and gmalloc take 24.7, and memalloc take 24. So memalloc by Microsoft is the best in this scenario. Also, the memalloc uses most memory, so this needs to be taken into account, but just these are large numbers, so it's not that much. And the performance improvement for the allocator comes from both decreasing the time needed to perform malloc and free, and also better data locality. Because if you just count the numbers, if 27 seconds, and it takes around 10% of the 9% of the time, the whole program, then even if you completely eliminate malloc and free, we would get 24.5 seconds. And you see that mmalloc is even faster than that. So one of the performance improvement comes from better data locality. Questions? No questions? Moving on. Okay, this closes the talk about memory, this closes the topic of the performance of memory allocation. And I hope you're finding the talk interesting, and I hope I'm not talking too fast and you can follow me. So next thing we will talk about is the performance of memory access. So if your program allocates and deallocates a lot of memory, the performance of the allocator will be important for the overall speed of your program. However, this is not often the case. Your program's performance very much depends on the way you access your memory, and that specifically means on the way how you lay out your data in memory. That's one thing. So is it in a continuous block or is it scattered around memory? And the second thing is, what is the access pattern to your data? So if you have a vector and you're going linearly through the vector for element 0, 1, 2, 3, 4, 5, it's much better for performance than just randomly jumping around memory. Even though it might seem, in the matter of from the performance point of view, it might seem the same. It's completely different if you measure the run times. So the simple abstractions of malloc free, new or delete, that doesn't take into account the underlying hardware, doesn't cut it for high performance software. You can achieve the highest performance only if your data structure or algorithm knows how the allocator behaves. You need to break the abstraction between the data structure or the allocator and the allocator. So this will make all optimal. Okay. So question, why does the program speed depend on the memory access pattern? Memory speed is a bottleneck on modern system, and it's becoming more and more of a bottleneck. So CPU can wait around 200 to 300 cycles waiting for the value it needs to be fetched from the memory to an internal CPU register. This is the time that CPU could do 200 to 300 simple instructions. To fix this, CPU designers introduced a small on-CPU memory called the cache memory. This is a really small memory, so it's typically, so it's really fast and it's really small. It's typically a few megabytes, but the access time is much faster, between 3 or 15 cycles per access. The CPU keeps the data it is currently using in this cache memory. So every access to the main memory begins by data being fetched from the main memory to the cache memory. The data the CPU is currently using, it's called a data set. And you want most of your data set to be in the data cache. No questions, moving on. Cache memories. So what are the principles of cache memories? So as I already said, every access to main memory begins by checking if the data is already present in the data cache. If it's in the data cache, it can be accessed really quickly. Otherwise, the CPU needs to wait these 200 to 300 CPU cycles for the data it needs to be fetched to the main memory. If the CPU doesn't access data for some time, the modified data, the data that it didn't access, modified or not, is returned back from the cache to the main memory to make space for new data. This process is called eviction. Okay, here an example of cache memories and data locality. We have a program that's performing 64 million searches on a hash set. So this is STD unordered set. There are 3 hash set sizes: small, which has 32 entries, medium, which has 1 million entries, and large, which has 64 million entries. So we're performing 64 million searches on 3 sizes of hash sets. Now, the runtime. If it's a small hash set with 32 entries, it takes 1.5 seconds to do all the searches. If it is a medium hash set, which has 1 million entries, it takes 2.8 seconds. And if it's a large hash set with 64 million entries, it takes 5.9 seconds. So the difference is 4 times between the small hash set and the large hash set. So the larger the hash set, the smaller the chance that we will access this. So what's the difference in speed? The larger the hash set, the smaller the chance that we will access the same data again before it gets evicted from the cache. This applies to all random access data structures. So if you're accessing arrays with random access, you're accessing hash set, hash maps, or trees, it applies to all of them. Questions? No questions, moving on. So the second part of the cache memory is the prefetcher. So if your program has a predictable access pattern, typically if it's iterating linearly over a vector of objects, the cache memory prefetcher figures this out, and it can preload data before the CPU even needs it. This is the part of the component in the CPU that's called the data cache prefetcher. So the programs that access memory in a predictable fashion see major improvements in speed. So here is an example of cache memories and their prefetcher. Imagine there is a program that's summing up array that contains 100 million integers. So we can sum it up by going 0 over the array by going 0, 1, 2, 3, or we can go strided. So we are summing 0, 16, 32, 48, and so on, or we can do a random. We can just jump through the array randomly. So if you're doing this sequential, if you're accessing the array of integers sequentially, the runtime is 180 milliseconds. If there is a stride of 16, the runtime is 740 milliseconds. And if you're accessing this huge array randomly, then the runtime is 6.6 seconds. So the worst case scenario is when you're doing the random accesses. So the prefetcher works with sequential and strided memory accesses. With random, it cannot do anything. So there is a point in keeping the memory access pattern regular. Okay, Jonathan asked a question: why is this strided memory access pattern slower? And I'll talk about that a bit later. Okay. Next is about cache memories, the cache line. So cache memories are divided into cache lines, and on modern systems, almost all modern systems, it's 64 bytes in size. There's some high-performance systems that have larger cache lines. Each line in cache corresponds to a block of the same size in memory. So 64 bytes in cache correspond to 64 bytes in memory. And there is one-to-one, there is a correspondence that the memory block has exactly one place in the cache memory. It cannot, or maybe not. I'm not sure. Okay. So if you access 1 byte inside the cache line, that means that the whole cache line will be fetched to the cache. So if you have a block of 64 bytes, you access 1 byte, the whole 64 bytes are really cheap to get. So they're really, really cheap to get. It doesn't cost you practically anything. So what if you want to benefit from the cache line organization, you need to organize your data so that the data that you're accessing together is too close to one another in memory. So if you have a class, and in each class you have your data members, you will profit if you put the data members you access together, you put them next to one another, so they get laid out in memory one after another. The next thing you want to do, you know that the CPU loaded the whole cache line from the memory to the cache. So you want to use all the data that is available to you. So you don't want to load data to the cache and then just use fraction of the cache line. You want to use the whole cache line. Okay, here's an example of cache lines and cache line performance. So let's say we have an array containing 100 million integers. Now, we are accessing them with stride. So stride 1 is we are accessing elements 0, 1, 2, 3. Stride 2, we are accessing elements 0, 2, 4, 6. Stride 3, we are accessing elements 0, 3, 6, 9, and so on. So what percentage of the data actually we use. So we load the cache line, but in case of Stride 1, we use 100% of the data from the cache line. The whole cache line, we use it. And the runtime is 180 milliseconds. As the Stride grows, the performance gets worse. So 210, 240, 270 milliseconds. Why? Because we're using the less and less data from the cache line. So with Stride 2, we are using only 50% of the data. With Stride 3, we are using only 33% of the data, and so on. Now, there is a fixed bandwidth between CPU and the memory, and the memory can provide data only the amount of data that the memory can provide to CPU is limited. And as the stride of the accesses grows, so the memory bandwidth becomes the bottleneck. So I wrote this. It is really a sin to load data into the cache line and then not use it. Okay. Question by Jason: will the prefetch perform the same if the sequence is reversed? Yes, the prefetcher works both if you go from 0 to n, from n to 0. There is no difference there. Now let's make a summary. So we talked about some cache memory properties, and now let's make a summary about memory access performance. So CPUs always work with simple types. They work with char, integers, doubles, and floats. From the performance point of view, the dependence between the memory access pattern and the access speed looks like this. If you have sequential accesses, you're accessing neighboring simple types. This is the best for performance. And you see here an example. There is this vector of integer, and then you're summing it. This is the best for performance. Next is the strided access. It's not best, but it's not as bad as random access. So you're accessing simple types in a vector of class. You're accessing a simple type in a vector of class instances. So the performance here, so you have a class and you're accessing one data member inside that class, one simple data member, which can be a character or an integer or a float, doesn't matter. And you see this in example. It's a vector of rectangles. Rectangle is a class. And then you're summing all visible. You're counting the visible rectangles. Now, the bigger the class, the bigger the stride. So the stride corresponds to the size of the class. And the bigger the class, you'll see later worse the performance, the slower your code is. And the third memory access patterns is random access. You're randomly accessing objects in memory. This happens if you're using std set, std map, std list. So using this random access data structure, fast random access data structures. Or you're accessing an object through a pointer. So example of set, if you're iterating over a set, that's not the best thing to do. And the second thing is you have this class car, which has a pointer driver. And then you're dereferencing this pointer inside of class. If you allocated this member using unique pointer, for example, or just new, basically have random access here. So your program will suffer performance issues. Okay, questions. Alexander Becherikov, can you clarify what you sum only elements on position divisible by stride, or do you also have loop over the remainder by? I don't understand this one. Can you please rephrase it? A similar question to Alexander. Is the comparison of what it takes to arrive at the same sum, or a comparison of summing the same number of elements with varying? Okay. I don't understand the questions. Is this a comparison of what it takes to arrive at the same sum or sum the same? So this is the comparison of memory access performance. So there are no numbers, but just for you to know, if you have a sequential access, it will be really fast. If you have strided accesses, which typically happen when you answer your programs as part of classes, this will be slower. And if you have a random access, then if you have random access, it will be much, much slower. Matthias Billiger, I think he wants to know, do you sum up the same amount of integer? So I don't understand. Is this question related to this slide or to the previous slide? Tim, can you unmute Jonathan?
Hi.
Hello. Hi. Yes.
So I'm just trying to understand this slide and the previous set. Is the comparison here between is it always, yeah, so in this case, is it always 4 elements and it's just 4 elements with different locality, or is there some, like in the stride 1 case, are you going like all the way to 12 like you would in stride 4, for example?
In stride 1, I go from 1 to 100 million, and with stride 2, I go again. I sum in all 4 examples. I sum 100 million integers. Just I'm summing 0, 1, 2, 3, 0, 2, 4, 8, then go to the end of the array. Then I start over. Then I start 1, 3, 5, the elements I missed. With stride 3, I go 3 times through the array. Okay.
Okay. Awesome. Thank you.
No problem. Any other questions? Can you unmute Alexander Becherikov? Hello, Alexander.
Hi, yes. By the remainder, by stride, I meant what you just said. You go starting from 0, then starting from 1, then from 2, and so on.
No, stride means the difference between neighboring elements. So
yes,
stride 1 is 0. Stride 1 means 0, 1, 2, 3. Stride 2 is 0, 2, 4, 6. Stride 3 is 0, 3, 6, 9, and so on.
That's okay. Right. And with stride 3, you need to start from 0, then start from 1, then from 2.
Yeah. I need to go to the array 3 times.
And these are the remainders by 3.
Yes.
Okay, thank you.
No problem. Okay, that's it. Okay. So this is a small experiment with class size and member layout. So this is a class called rectangle, and it has 2 important members. One is mVisible, and there are point 1 and point 2. And I also added these paddings. One is between visible and point 1, and the other one is at the end of the class. So there are 2 functions that work with the vector of rectangles, and they go through the vector of rectangles. And one is called calculate surface visible. It checks if the rectangle is visible by accessing this mVisible, and then it adds its surface to the accumulator sum. The other one, it's not depicted here, but it's simple. It's called just calculate surface. It goes through calculate surface goes through all the rectangles and calculates their surface. So the difference is that the calculate surface visible accesses only all 3 visible P1 and P2, 3 members, and the calculate surface accesses only P1 and P2. It doesn't access visible. Now, as far as performance is concerned, here are the numbers. So first, the question is how the speed of processing data depends on the size of the class. So the red one is calculate surface, and the blue one is calculate surface visible. And if you see if the class is smallest 20 bytes, the runtime is about 30 milliseconds. And worse, if your class is 184 bytes, then the runtime is about 140 milliseconds. So it's 4 times slower. The same phenomenon is observed with the calculate surface visible. So originally, for the smallest class size, it takes 110 milliseconds, and for the largest, it takes about 200 milliseconds. So if you have your code and you say, okay, this thing used to work 6 months ago, good, so it was okay, the performance was fine, but now it's not. And you might want to ask what happened between now and 6 months ago. One of the reasons why your code might be slower is because somebody added additional data members. Next is experiment with class size and member layout. So if you remember, between visible and point 1, there is a there is padding. So we change the size of that padding to see how it influences performance. The class size is fixed, 248 bytes. In the case of calculate surface sol, we are not accessing the visible member. So we are not accessing the visible member. So this padding doesn't have any influence. You see that the performance doesn't depend on the padding, but for the calculate surface visible, as the padding between the point one and surface and visible grows, so the performance goes worse. So the optimum case it's 200 milliseconds, and the worst case is 250 milliseconds. Jason asked, are both of those tests using the same rectangle data structure? Yes, they're using the same rectangle data structure. So you see that just the class size and the layout of your data members can have an impact on performance, and not a small impact, quite a significant impact. So next, so principles of cache-aware software design. If you want performance, you must be cache-aware. So what does it mean to be cache-aware? Make data access predictable. So if you're iterating over a vector of objects, iterating over a vector of objects is almost always faster than iterating over a vector of pointers. Precisely for this reason, when you're iterating over pointers do not necessarily point to the neighboring locations in memory. And the prefetcher is clueless, it doesn't work, and your program is slow. If you need to use your fast access data structures, use them sparingly. So in case of sets, so hash maps and trees, the CPU needs to chase pointers. Just the referencing a pointer basically represents a random memory access. And for example, for binary trees, you need to do them several times. The memory access in this case is unpredictable, and the hardware prefetcher is powerless. If your class contains pointer to other heap allocated class, it can suffer from low performance when you dereference the pointer, when you want to access the class and its member. One of the things you don't want to do is not use linked lists. If your program is using linked lists are great as a concept because they're very flexible. Iterators are stable. You can insert, remove anywhere, but they're bad for performance because of this memory chasing. But normally, programs almost never use all the possibility of a linked list. So normally, program will just insert everything at the beginning and then remove some elements or some kind of specialized pattern. So in that case, you can try some arrays-based alternatives, colony, bucket array, or a gap buffer, or you can use std list with a custom STL allocator. That works also, but it's not as fast. No questions? Oh, here's an image displaying array of pointers. So you have std vector, which is a pointer to the vector of base class pointers. And this is an optimal layout. So this is a layout in memory. And you see that the neighboring pointers point to the neighboring elements classes in memory. This is good. Actually, this is good for performance. But the bad thing about this is that there is no guarantee that you'll get the optimal layout. Actually, if your program is a long-running one, it might happen that you get a non-optimal layout. So this is the non-optimal layout. And the first pointer points to the fifth element, and the second pointers point to the second element, and so on. So how does questions? If I use instead of pointer, for example, index to another container, is it better way to use than to use pointers? Yergush asks. So it works like this. If you have a class, for example, imagine you have two classes. You have a large class, you decide to split it in two classes. If you keep class one in one vector and keep the second class in a second vector, and you're iterating over the first vector, and then you're dereferencing a pointer, but you're always dereferencing the neighboring elements in memory. So there is no problems with pointer in that case. Okay. Second question: what should OS kernels use instead of linked list to represent the file system? That's a complicated question. I cannot answer that question right now because it involves a lot of investigations. Matthias Billiger, is this only valid for some type of objects types or just the order of the object? So the importance is the order. So if you're doing like a raw measurements and you create your class and then you allocate, you call new on the elements of the allocator, typically when the system just starts, the allocator will return neighboring memory chunks. But if your program has been running for some time, and this some time can be 1 second, so not long, and or you're deleting and modifying the container, in that case, you can easily get that non-optimal layout that I was talking about. So let's compare array of values versus array of pointers. Arrays of values are much better for performance compared to array of pointers. All memory is allocated in a single block, so there is no cost to heap. We already talked about that in the talk about the performance of memory allocation. If you're accessing objects sequentially, you get sequential memory access. This is perfect. There is no virtual dispatching mechanism to slow things down. Virtual dispatching comes with a performance price, and it's not a small one. It can be really high if you are not using virtual dispatching correctly. It also enables small function inlining, which increases performance. Downside is no polymorphism. For speed, you should prefer arrays of values instead of arrays of pointers. Okay. Now here's the measurement of performance array of pointers. So the source is here. There is a vector with 20 billion objects, and we call a small virtual functions on it or a large virtual function on it, which does many computation. If you have a perfectly optimal layout, the small virtual function takes 384 milliseconds. If you have a perfectly non-optimal layout, so all the data is scattered in the memory, you get 5 seconds. So it's almost 20 times slower. The large virtual functions is the perfectly optimal is 2.6 seconds and perfectly non-optimal is 16.9 seconds. The price is lower here, but it's still high, okay? And the performance of your program will be typically somewhere between those two numbers. So it can be really fast if you're lucky, or really slow if you're unlucky. If you're doing many, if you're moving around pointers in the array, or the data structure is a long living one, for example, data structure that lives several hours, you can get really bad layouts. Why asked? Is there any kind of limit after which sequential order won't kick into effect? Think really big classes with complicated logic. There is a hardware limit on how many. There is a hardware limit. Prefetcher can works with streams of data, so there is a limit like 5-6 streams. So if you're processing 5 or 6 or 10 vectors simultaneously, it might happen that the prefetcher won't kick in, but I don't know the details, so you need to figure out, you need to measure that. Okay. Second principle of cache-aware design. So you have the whole block of 64 bytes loaded into data cache. Don't let that data in cache go wasted. So one of the things is you should keep your classes small. We explained already why. You should keep the data members they use together. You should declare them in the class together. Everything else that so if your class is really on a hot path, you are processing a lot of instances. In that case, you should investigate of moving all unused members of that class or rarely used to other classes. You want to load data from the memory to the cache only that you're actually using. Data loaded into the cache that is not used is wasted performance opportunity. As I already said, declare data members you access together close to one another in the class. What you also want to do is you want to keep your small classes in a dedicated vector. You don't want to process small classes as part of the larger classes. That kills all the performance impact, all the performance improvement if you process small classes as part of the larger classes. Okay. Now, here's a memory layout, small versus large classes. So how does it look like? So do you remember the rectangle class? So here the blue one is the visible attribute, the green one is the P1 is point. White is unused data members. Unused meaning that you're not using them for the current processing. And the orange is the cache line. If you have a small class, this is the layout. So basically everything you load into the cache line gets used, and this is perfect for performance, although not always possible. If you have a large class with unused members at the end, see what happens. So this class takes 2.3 cache lines. So that's a lot of space. And you see that first chunk of data is the cache line 0. Second chunk is split between the second class that you're actually accessing is split between cache lines 2 and 3. The third one is split between cache lines 0, 1, 2, 3, 4, and 5. So this is not optimal for performance. If you have a large class which has unused member both in the middle and at the end, it gets even worse. So visible of the class of instance 0 is in the cache line 0, and the P1 is the cache line 1. And then visible of the instance 1 is the cache line 2, and the point is in the cache line 3. So this is really bad for performance. You're loading a lot of data into the cache line that you're not actually using. Now, object-oriented paradigm in C++ can be inefficient from the performance perspective. Doesn't mean that it is necessarily inefficient, but it can be. Why? You have containers of pointers. You have containers containing objects of different types. You have large classes, and you have classes that have members that point to other heap allocated classes. In game development, they use another paradigm called entity component system. What they do there, they get rid of large classes. They get rid of inheritance. Instead of inheritance, each, let's say, entity contains of components. So components are classes, and you have several one entity consists of several components. For example, you have a car which consists of engine and wheels and steering wheel and so on. So it consists of components. The components are processed independently of the entity they belong. So all the wheels are processes independently of the car. So it doesn't matter if the wheel belongs to a car, to a bus, or it belongs to a toy car, it will be processed independently as part of a dedicated vector. The good thing about this approach is that entity can change its type at runtime. It's really easy to add new components to the already existing entity. So if you have a car which has 4 wheels and somehow there is a car with 3 wheels, then you can do that easily without recompiling or changing the class of your program. Personally, I don't think the world is moving toward entity component system, but there are some nice principles that can be useful in all programs if the speed is important. Okay. Next, principles of cache-aware software design. The whole block of so I already said the whole block of 64 bytes is loaded into data cache. Don't let data in cache line go wasted. If you need to use trees, prefer n-ary trees to binary trees because they use cache lines more efficiently. What happens? A binary tree has a pointer to the left and right, and then you have the actual value, and it uses maybe half of the cache line. And the n-ary trees, they use more. So they can use the whole cache line. And this is better cache line utilization. Since they're shallower than binary trees, there is a shorter path between the root and the leaf node, so less pointer dereferencing, less random access, memory accesses. Don't store pointers in a hash map, store whole as objects. So this tip is more for a hash map. So if you have pointer in a hash map, when you're loading an object, you're just loading pointer, then you need to dereference the pointer. If you keep a whole object in a hash map, then when you access the first byte of the cache of your object, there are many other data members that will be loaded as well. You can also use cache-friendly hash maps that are based on open addressing scheme. In case of collision, they perform better in terms of data cache misses. Now, I'm not going to explain about open addressing hash maps. They have also drawbacks. If you need this one, you should Google it. Okay, next, an example. This is an interesting example, a binary tree example. So we have a binary tree, which is a data structure used for fast lookup. You want to check if the value is present in the binary tree, insert or remove it. So this is a binary tree. Let's check if 7 is in the binary tree. So we start from the root. 7 is less than 8. If the number we're searching for is less, we go left, otherwise we go right. So we go left. 7 is larger than 3, we go right. 7 is larger than 6, we go right, and here is 7. So it is in the binary tree. So this is how binary tree works. How they're internally represented is with this struct. So there is a value that's held in the binary tree. There is a pointer to the left node and pointer to the right node. So the problem is that binary tree is not, memory is one-dimensional, it's a vector, and binary tree is two-dimensional. Now, question is how to optimally represent this memory structure in memory. Here are 3 examples. So this is the binary tree we're going to use as an example. So if you want to lay it out in memory, there are basically 3 orders. One is called the breadth-first search layout. So if you remember from our algorithms and data structures, so how does it work? We first put layout members on the level 0, so we put the 8. Then we put members on the level 1, so we put 5 and 11, 5 and 11. And then we put members on the level 2, so we put 3, 7, 9, and 13, 3, 7, 9, and 13. There is a depth-first search layout. So we first we visit the tree in the depth-first search. So, and we lay it out in memory in that way. So first is 8, then 5, then we put 3. We go back, we put 7, we go back, we put 11, then we put 9, and eventually put 13. Or there is a random order, it doesn't matter, we just scatter them around the memory. Now there is a poll I prepared. Which is the most optimal layout to check if the given list of values is present in the tree? Which is the fastest layout? So can you show the poll? Okay. You can vote here. I'm just curious what the people will say. So these are the poll results. So BFS, DFS, so it doesn't matter, 14%, DFS layout is 41%, and BFS layout is 46%. Now the answer is that the fastest is the depth-first search layout. Now you might wonder yourself why, and the reason is really simple. In the depth-first search layout, DFS layout, the left side, the left node is always the left node is always neighboring in memory. So if you look at the DFS orders, 8 and 5 are neighbors, and they're also neighbors in memory. 5 and 3 are neighbors, and 5 and 3 are also neighbors in memory. 11 and 9 are neighbors, and they're also neighbors in the memory. So the left side will be neighbor in the memory. The right side won't be neighbor in the memory. And that's the reason why DFS order is faster. Now the question is there any as a more optimal layout? And actually there is. I'll learn about that later. It's called Van Emde Boas layout. And what you're laying out a node left and right together in memory. So in this case, 1, 2, 3 will be neighbors in memory. 4, 5, 6 will be neighbors in memory. 7, 8, 9 will be neighbors in memory. Okay, so this is even better than the depth-first search layout. Here's the lookup performance. We created a perfect binary tree from a sorted array. It's perfectly balanced. Memory is allocated by calling malloc on a dedicated allocator. So we have a guarantee that we'll get neighboring memory chunks. And we use 3 kinds of allocators actually. So let's see the optimal allocator. BFS layout is 11.2 seconds, DFS is 7.2 seconds, and Van Emde Boas is 6.4 seconds. That's for the optimal allocator that returns chunks in the way they are neighboring chunks. Calls to malloc return neighboring chunks. The STD allocator is a bit slower. And the reason is actually it's not returning neighboring. It also returns neighboring memory chunks, but the reason is because the chunk itself has some metadata before it. So it's the data cache utilization is not as good as this one. So even two neighboring chunks, there will be a small padding that you don't see, but they will be there, and it decreases the efficiency of the cache line. If you have a non-optimal allocator, just returns random chunks, you see that the performance is really bad. And for 14.4, 14.3, in the case of BFS layout, it's even worse. Okay. So lessons learned. We gain performance if. So in this case of binary tree example, if we allocate a dedicated block of memory for the data structure. So if you have a dedicated block, that means you increase the likelihood, you decrease the data set size, and you increase the likelihood that the data you're accessing will be in the cache. You can achieve this only with a custom allocator. So this kind of guarantee can be only made with a custom allocator. Additionally, for the binary trees, you can create an allocator that doesn't have any metadata. So this is an added benefit. You try to keep the block of memory allocating from as compact as possible. So this is easy to do with the custom allocator. This increases data cache hits rate. We take advantage of cache line organization. So if two nodes are adjacent in the binary tree and they're adjacent in the memory, there's a high probability that they will share the same cache line. If they share the same cache line, we get access with no cache misses. What are the other ways to gain performance in this example? So one of the ways is to keep the struct node, a struct that internally holds the data, as compact as possible. This again increases the likelihood that two or more nodes share the same cache line. On a 64-bit system, the 48 bits of the pointer are actually used. Then you can combine two pointers to decrease the size of struct nodes. So instead of using 8 bytes, they will use 6 bytes. Sometimes this can help. If you recompile your program, which has many cache misses, to a 32-bit system, they can improve the performance because it uses smaller pointers. You can also increase performance by for the binary tree by using std vector as an allocator for the tree. And the good thing about this vector is that using std vector is you don't have to use pointers. You can just use the offset from the vector beginning. So the elements, the chunk will have 0, 1, 2, 3. It won't be just random addresses in memory. I don't see any questions here. So moving on. Next, we talk about binary tree modifications. So as you add or remove nodes, you slowly make your memory layout less and less optimal. And after some time, the access becomes slower and slower. So there are several solutions to this. One is to recreate data structure, which is optimal, again. The second one is to perform some kind of defragmentation on the existing data structure. The third one is not to delete the nodes. You keep them around for some time so they can be reused if opportunity arises. All of this takes time, but can make your long-running program faster. Okay, this finishes the talk about binary trees. I don't see any questions. If you have any questions, feel free to ask. Okay. Next example is called about a hash map example. This is an example hash map that uses an array to store its values. So this is an example. Each entry of the hash map has a count, and there is an array which is a pointer. There is a pointer to array, which holds the actual value. Inside each element of the array, there are, okay, I already said that. So most of the times in the hash map, the entry, there will be 0 or 1 element in the in this array. If you have 2, that's collision, but normally hash maps try to avoid collision. Now, what's the problem with this approach? Let's see. Well, the problem is here. Exactly. The problem is the same as the problem as recommendation. Don't store pointers to objects in your hash map. So every time you access a hash map, which is a hash map bucket, which is basically a random memory access, you have another pointer dereferencing, which is another random memory access. So you have 2 random memory accesses. An optimized version will take advantage. They take advantage of the knowledge that we are most of the time storing 0 or 1 element in the hash map. So you see here that if there is count is 1 or count is 0, there is no array doesn't point to anything. Only if the count is 2, then the array will point to a externally allocated array. This also decreases memory fragmentation because here we have allocated 3 memory blocks. In this case, we have allocated only 1. So what is the lookup performance? We are accessing 64 million entries. So we have a small load with 32 entries, medium load with 1 million entries, and large load with 64 million entries. So hash map with 64 million entries. So if you are doing 64 million accesses, the simple hash map takes 5.8 seconds. The optimized takes 3.7 seconds. And you can compare that with the STD unordered set. This is the measurement I did on Linux. For the small data sets, you see for a small load, you see that doesn't matter. The STD unordered set is equally fast as the optimized hash map. But as the size grows, as the size of your data structure grows, the impact of data cache misses becomes more and more visible. Okay. What map is the optimized cache map? So, this is the experiment I did. So the implementation looks exactly like in this picture. I forgot to put a link here, so I have it in repositories. If you want, just send me an email and then I'll ask you. But the implementation is exactly like this one, so nothing fancy. This is the right is the optimized one, and the left one is the let's say how it's simple hash map. Okay. Finally, principles. Okay, have you looked at things like the Robinhood hash implementation? No, I haven't. I don't have an idea what's Robinhood hash implementation. So Jeff, after this talk, feel free to stay, and I'm eager to learn on GatherTown. That's it. Okay. Principles of cache-aware software design. Don't let the data you will reuse in the future get evicted from the cache. That's also one important aspect. Most of the things we talked about is related to cache line utilization, but you don't want to evict the data from the data cache that you are. You want to reuse it as much as possible. Don't let the data get evicted. Don't iterate the same container 2 times. So you have a container of objects, and with the STL algorithm that can happen often, that you're iterating the same container 2 times. Don't do that. Now the question is how to do that elegantly, but bear in mind that this can have implications on performance. If your program is performing many random accesses to increase the likelihood that the same data is not evicted from the data cache, try to decrease the size of your data structure. This is either a binary tree, a hash map, or random access array. If you manage to decrease the size of your data set, that automatically means that you're increasing data cache hit rate. If you have a hot class, rarely use members outside of them. You can recompile your program for 32-bit systems. This makes pointers smaller, but again, these have other problems. Or you can rewrite the code not to use all pointers, but to use the offset from a fixed array. Okay. So let's investigate some of the tips I gave. Reiterating the same collection 2 times. For example, you want to find minimum and maximum in the vector. Class size is 64 bytes and it has 100 million elements. So if you're doing in separate loops, it takes 368 milliseconds. If you're doing in the same loop, it takes 207 seconds. Here's the example. If you compile the binary tree example we just talked about for 32-bit systems, the Van M. Du Bois layout on the 64-bit system takes 6.4 seconds, and on a 32-bit system, it takes 5.9 seconds. So it's not that huge performance in speed, but it is some. And for the other layout, it gets even better. Okay. Composable algorithms from the ranges libraries help to avoid extra memory traversal. Yes, yes. That is one of the major, for the performance C++, that's one of the major things, important C++ 20 feature that is added, an important for performance. Okay, this finishes the talk about the, Arnaud Desmarais says, know your algorithms, STD, min, max element. Yep, thank you. When not to optimize. Well, some of the techniques presented here will benefit only the cases with large data sets. So if your data set is small and it fits the data cache, you won't see any performance improvement. Actually, you might see performance degradation because your program is probably doing more work, executing more instructions. Binary tree optimization, hash map optimization only makes sense if the data set is large. So what is a large data set? The data set that doesn't fit the last level cache. On most CPUs, this is a few megabytes. Small data set is the data set that fits level 1 cache. On most CPU, this is 16 to 32 kilobytes. Data structured with a short lifespan that are created and destroyed really quickly also don't benefit from optimization a lot, because creating a memory optimal data structure takes more time than an average data structure. Also, if you do the defragmentation, it also takes more time. If your data structure is just used a few times and then destroyed, the overhead of creation will dominate the runtime. Okay. And that's it. Final words. Most of today's software is limited in speed, not because there's a lack of computational resources in the CPU, but because of the memory bandwidth. If you use your computer resources recklessly, the software can be much slower than it needs to be. With a careful design, you can help mitigate some of these problems. If the performance is important, you need to be aware of the memory hierarchy and the data caches, on how the data cache works if you want to maximally exploit the performance of your programs. If you're a performance enthusiast, Electronic Arts, the game developer, has its own implementation of STL that focuses on performance. There are many great ideas how to do optimization for performance-sensitive applications. Just Google EASTL for more information. Okay. The end. Thank you very much for this talk. Now, what now? After this talk, can we measure questions? Okay, question time. Can we measure the time the CPU is waiting for the cache to be filled? Any tool suggestions? So you cannot measure individually. Like in iteration 1235, did it take long or short time? You cannot do that. What you can do a statistic approach. That means that there are tools that can perform this measure and tell you how much CPU cycles are wasted because your program was waiting for cache, for memory from cache. The best one is the Intel's vTune. It will tell you how many cycles were wasted. There is also a command line version called PMUtools. PMUtools that does the same thing. It does the same thing. It's free, but both Intel vTune and PMUtools work only on Intel CPU. For AMD and ARM, I'm not aware of any good tools. You can use the perf on Linux, and I guess the other operating system have something similar. It can tell you which code has many cache misses, but it won't tell you what improvement to expect. Okay. I think Alexander Becheriko. I think most standard library implementation don't use SSO. Maybe even the standard has limitation. What is your reference for std string? Small string optimizations. I don't know. So the standard library implementation, I don't know. I don't work with standard libraries, so this is not. I double checked. There is this great book about C++, C++ high performance that was talking about std string implementation. So I could look it up. Join me later on the track C in the Gather Town so we can discuss. Thank you very much. So this was the talk. If you like it and you're interested in this stuff, feel free to go to my website and just apply. You can follow me on Twitter and you can also on LinkedIn, so you get when new blog posts are appear. Now we're moving to Gather Town, and there is a room called Track C. I will be there if you want to ask questions or we can discuss. Feel free to join. Thank you very much.